I want you to imagine, just for a second, that you are standing in your bathroom.
Okay.
And you're leaning in real close to the mirror, right? Looking directly into your own eyes.
So staring right in there.
Yeah, exactly. And if you stare closely enough at your pupils, the dark circles right in the center, you might expect them to look like perfect mirror images of each other.
Right, like they're operating perfectly in tandem.
Exactly.
Yeah.
But here's a genuinely surprising fact. Your two pupils are actually not perfectly synchronized.
Not at all, yeah.
At any given moment, one of them is usually just like a little bit larger than the other. And that tiny asymmetry, it isn't static. It constantly drifts and fluctuates over time.
Yeah, it is this microscopic, continuous dance happening right in front of us, and it's entirely beneath our conscious awareness.
It's wild.
Yeah.
Specifically, we're looking at young kids and asking, can the instability of this left-right pupil asymmetry reveal hidden information about attention-related traits?
It is a phenomenal question, honestly.
We're unpacking a brief research report published in Frontiers in Cognition. This was back in March 2026.
Right.
And it comes from a team of researchers in Japan, led by Sono Bukawa. They pulled together experts across, the Chiba Institute of Technology, the National Center of Neurology and Psychiatry, Nagoya City University, and SMK Corporation.
Yeah, it's a really solid cross-disciplinary team. And, before we get into the mechanics of eyeballs and autonomic responses, we really need to establish why this specific problem matters.
Right. Why are we talking about this?
Exactly. It comes back to how we identify early traits associated with ADHD.
Yeah.
The signs can appear very early, often well before age 5. And there is broad consensus that identifying a child's support needs early on, it dramatically improves their developmental trajectory.
But there's a roadblock, right?
A huge roadblock. Our current assessments rely really heavily on interviews and behavioral reports from caregivers and teachers.
Which, those are vital, obviously.
Oh, absolutely vital.
Yeah.
But they are fundamentally subjective. They are heavily swayed by contextual factors.
Like what kind of factors?
Well, think about it. The child's age, their sex, the family dynamic at that specific moment, or even just the cultural setting, all of that filters human interpretation.
Right.
Like a highly active child might be perceived as incredibly disruptive in a strict, rigid classroom environment.
But completely unremarkable in a playground or an unstructured play-based setting.
Exactly. It's all relative to the observer.
So the field is desperate for objective physiological markers.
Yes.
Something measurable that doesn't just depend on a human observer's interpretation of a kid's behavior.
Precisely.
Okay, let's unpack this. Because bringing up ADHD traits in this specific context, it actually highlights a massive shift in how neurodevelopmental research is being conducted today.
It really does.
Because, if ADHD is a clinical diagnosis, how are these researchers studying it in kids who haven't actually been diagnosed with anything?
That is the philosophical foundation of this entire study, actually.
Really?
Yeah. Historically, the medical model has treated ADHD as a strict binary. You meet the criteria or you don't.
Right. You're either in the diagnosed group or the control group.
Exactly. But the scientific framing has largely moved past that. Attention and hyperactivity traits are now widely viewed as continuously distributed across the entire population.
Okay.
So it is a dimension. It's a spectrum.
Which means every single person, including kids who are developing typically and have literally zero clinical diagnoses, they all exhibit these traits to varying degrees.
That's it. And because they adopted this continuous trait framework, the researchers didn't set up a traditional case versus control study.
Oh, interesting.
Yeah, they looked for a graded physiological signal within a group of completely typically developing children. They recruited 59 kids in total, 24 boys and 35 girls.
And their ages were 60 to 96 months.
Right.
So we are looking at 5 to 8-year-olds, essentially,
Right.
with the mean age right around 77 months.
Yep.
And none of them had any previously diagnosed neurological or developmental disorders.
Right.
And all of them had normal vision.
That's right. So to measure where these children fell on that continuous spectrum of attention traits, the researchers used the Japanese version of the ADHD Rating Scale-5.
The ADHD RS5.
Exactly. But crucially, they did not use it as a diagnostic threshold. They didn't use it to say yes or no.
Okay, how do they use it then?
They used it to generate percentile scores. So they looked at the total score, as well as the specific subscales for inattentiveness and hyperactivity or impulsivity.
Ah, okay. So across these 59 kids, those scores spanned the full range, from the 1st to the 100th percentile.
Exactly.
What's fascinating here is they completely flipped the traditional research model.
They really did.
They took a diverse group of neurotypical kids and mapped out exactly where they land on this dimensional scale. And then they started looking for a biological signal that scales alongside those traits.
Right, which is a much more nuanced reflection of human neurobiology, honestly.
Yeah, it makes sense.
But identifying the behavioral traits on a spectrum, I mean, that's only half the battle. They needed to see if those behavioral percentiles correlated with something happening in the physical body.
Which brings us back to the bathroom mirror and the pupils.
Yes, back to the eyes.
Because when most of us think of attention, I feel like we think of the prefrontal cortex or, I don't know, complex neural networks.
Right.
The little black dot in the center of the eye doesn't immediately come to mind as the seat of attention?
No, it doesn't. But in neurophysiology, the pupil is actually highly regarded as an indirect window into a very specific, deeply embedded part of the brain called the locus coeruleus, or LC for short.
The locus coeruleus.
Right. It is a tiny nucleus in the brainstem, but it is the primary source of noradrenaline for the brain.
Oh, wow.
Yeah, and it plays a massive role in regulating your arousal, alertness, and attention.
So the LC is essentially the brain's central alertness node.
That's a great way to put it. And it is intrinsically tied to the autonomic nervous system.
Okay.
The sympathetic pathway, which drives your arousal, causes pupil dilation.
Right, fight or flight.
Exactly. And the parasympathetic pathway, which drives your resting state, causes pupil constriction.
Rest and digest.
You got it. And the LC sits right at the center of this push and pull dynamic. As the LC modulates your arousal, those minute neural fluctuations are mirrored by the smooth muscles controlling the diameter of your pupils.
Okay, I love this. It's like the pupil is the dashboard indicator light for your car's engine.
Yes. Perfect analogy.
Right. Because staring at the dashboard light, it doesn't physically show you the pistons firing inside the engine block.
No.
But it tells you exactly how hard the engine is revving in real time.
Exactly.
And practically speaking, I have to imagine trying to read a dashboard indicator is infinitely easier than trying to put a squirming 5-year-old into an MRI scanner.
Oh, the practical utility cannot be overstated.
Yeah.
I mean, eye tracking is non-invasive, it requires no physical restraint whatsoever, and the data capture is immediate.
That's huge.
Yeah.
Let's look at their experimental setup, actually, because the elegance is really in its simplicity.
It really is.
Like you said, no chin rests, no bite bars, no heavy restraints to keep their heads perfectly still. The kids simply sat back in a comfortable chair with a caregiver sitting right next to them to keep the environment totally relaxed.
Yeah, they wanted them comfortable. And they utilized a toe bi-profusion eye tracker for this.
Okay.
It basically just sits right below a monitor and records the diameter of both pupils simultaneously. And it does this at a rate of 120 samples per second.
Okay, at 120 hertz, you are capturing truly microscopic variations.
Oh, yeah.
And the visual task they used was incredibly straightforward. The screen just displayed an animated red smiley face to capture the kid's gaze, drawing their attention right to the center of the screen.
Right.
And once the tracker confirmed the child was actually looking at it, the animation stopped. It just became a static red face on a gray background for up to 15 seconds.
And if the child looked away, the trial just ended. It reset, and the animation returned to pull their gaze back.
Smart.
Yeah, and they ran this cycle up to 10 times for each child.
Okay, so after running the trials, filtering out all the noise, and interpolating the data to account for natural things like blinks, the researchers were left with an average of about 90 seconds of highly usable pupil data per child.
Right.
And they parsed that into half-second epochs.
So you have 90 seconds of really high-fidelity data, capturing the diameter of both the left and right pupils at 120 frames a second. The researchers had to distill that mountain of data into specific metrics, to see if any of them actually contained a signal that correlated with those attention trait percentiles we talked about.
Right, they couldn't just throw the raw data at an algorithm and hope for the best.
No.
They computed 4 very distinct metrics. And the most obvious starting point is just the overall size, right?
Yeah.
So measure 1 was simply the average pupil size across both eyes during that 90-second window. They called this LR.
Right. And if you have an average size, well, you can also measure how much that average size fluctuates over the course of the recording.
Makes sense.
That gives you measure 2, the temporal variability of the average size, or VarLR.
Okay, so those first 2 metrics treat the eyes as a single unit, essentially, looking at the overall size and the overall fluctuation.
Exactly.
But this study is specifically about asymmetry. So for measure 3, they looked at the average difference in size between the left pupil and the right pupil, the interocular asymmetry, which they called VarLRdiff.
And finally, measure 4 looks at the instability of that asymmetry.
Wait, meaning what?
Meaning not how different the pupils were on average, but how much that left-right difference moved around and fluctuated over the entire 90 seconds.
Oh, okay.
The temporal variability of the left-right difference, VarLRD.
VarLRdiff. Okay, here's where it gets really interesting. Because the researchers took these 4 specific physiological contestants, basically, and ran the statistics against the caregiver ratings on the ADHD scale.
Yeah.
And exactly one measure survived statistical scrutiny. Just one.
Just one. The variability of the left-right difference. VarLRdiff
showed a modest but statistically reliable positive correlation with the total ADHD trait score. The correlation coefficient, or rho, was 0.35, with a p-value of 0.007.
And it is really worth noting here that it didn't just track with the total score, it actually correlated significantly with the specific behavioral subscales too.
Oh, really?
Yeah, it showed a correlation of 0.40 with inattentiveness and 0.29 with hyperactivity and impulsivity.
And this wasn't just some byproduct of demographics either. They controlled for age and sex, and VarLRdiff held its ground regardless of where the kids fell in that 60 to 96-month window,
Right.
or whether they were boys or girls.
Exactly. Meanwhile, the other 3 measures essentially flatlined.
So basically nothing.
Yeah, statistically speaking, they showed no meaningful relationship to the attention traits at all. The entire signal lived in how much the asymmetry fluctuated.
Okay, the obvious question here is why? I mean, why would the instability of a microscopic mismatch between the left and right pupil be the sole metric that correlates with attention traits?
It's a great question. The authors synthesize a biological hypothesis based on 2 interacting mechanisms: hemispheric imbalance and neural crosswiring.
Okay, let's break those down.
Sure. So we have known from previous neuroimaging studies that individuals who exhibit strong ADHD traits often show structural and functional differences between the left and right hemispheres of their brain.
Right, that's pretty well documented.
Yeah. And that lateralized difference actually extends deep into the brainstem, affecting our old friend, the locus coeruleus.
So the left and right hemispheres of the alertness center might actually be operating with a slight asymmetry themselves.
Exactly, but that alone doesn't explain the pupils because of the second mechanism, the wiring.
Okay.
The locus coeruleus doesn't project a simple, isolated signal straight down to the eye on its own side. It projects complex signals to a secondary relay station called the Edinger-Westphal nucleus.
The Edinger-Westphal nucleus.
Right.
And that nucleus contains the parasympathetic neurons that actually innervate the pupillary sphincter muscles, right? The ones that constrict the pupil.
Right, you got it. But here's the critical part. The locus coeruleus projects to both the ipsilateral and contralateral portions of the Edinger-Westphal nucleus.
So it crosswires.
It crosswires. It sends signals to the same side, and it crosses over to the opposite side.
Oh, wow.
Because of this complex bilateral input, if the locus coeruleus activity is highly imbalanced between the left and right hemispheres, that crosswiring can actually manifest as an asymmetry in pupil constriction.
Okay, that perfectly explains why an asymmetry exists in the first place. But it doesn't explain why it was only the fluctuation of that mismatch that mattered in these specific children.
Right. And that brings us to the developmental age factor.
Okay.
In 5 to 8-year-olds, the autonomic nervous system is still highly immature. That push and pull between sympathetic arousal and parasympathetic calm, it just hasn't fully stabilized yet.
Makes sense. They're kids.
Exactly. And because the system is immature, this left-right asymmetry doesn't present as a stable, constant difference. It emerges, it vanishes, it drifts around.
And the hypothesis is that in kids with stronger ADHD-related traits, whose autonomic regulation might be even more immature or unstable, this fluctuating asymmetry becomes significantly more pronounced.
That is the core argument, yes.
Yeah.
The instability of the pupil mismatch is essentially a surface-level broadcast of an unstable, lateralized autonomic regulation happening deep in the brain.
Which also beautifully explains why the other 3 measures completely fail to show correlation.
It does.
Like, take the overall average pupil size. Young children naturally have larger pupils than adults do because of their baseline autonomic state. So that creates a physiological ceiling effect. If the pupils are already dilated near their natural maximum, the average size metric is effectively maxed out. It just becomes totally insensitive to subtle differences between the kids.
Yeah, and the same developmental logic applies to why the average left-right asymmetry failed too. Interestingly, average asymmetry actually has been shown to correlate with attention traits in some adult studies.
Wow, really? In adults?
Yeah, but in young children, their baseline autonomic activity is so high and so noisy that it acts like static on a radio. That high amplitude background noise completely obscures the subtle signal of the average asymmetry. You can only see the signal in the temporal fluctuation.
What about the fluctuation of the overall average size, though? Why didn't that track with the traits?
Well, capturing the temporal dynamics of the average overall size requires a completely different mathematical approach. You can't just look at simple variance.
Why not?
Previous research suggests you have to measure the complexity and unpredictability of the time series data using these complex algorithms like sample entropy.
But sample entropy requires a massive continuous data stream to identify those complex patterns reliable, right?
Exactly.
And 90 seconds of usable data, which is chopped up by natural blinks and gaze shifts from a 5-year-old, that simply isn't enough data to feed that algorithm.
No, it's not. If we connect this to the bigger picture, we are seeing a physiological correlate that shifts depending on neurodevelopmental age.
Yeah.
The signal lives in the average mismatch for adults, but it shifts to the variability of the mismatch for children. That demonstrates that as the brain matures, the way it broadcasts its internal state changes fundamentally.
The neurobiology is incredibly elegant. But well, hold on, though. I got to play devil's advocate here.
Please do.
We're talking about a 5-year-old sitting in a chair. If you're measuring pupil fluctuations down to the millimeter, couldn't a high variability score just mean the kid was squirming in the seat? Or squinting because they were bored?
That is a critical point of skepticism, and it requires serious attention. Measurement artifacts are the bane of literally any study relying on temporal variability. Blinks, brief saccadic eye movements, head shifting, or even just a partly lowered eyelid changing the visible area of the pupil. All of that can inject artificial fluctuations into the eye tracker's raw data.
And naturally, a child who is exhibiting high hyperactivity and inattention traits is vastly more likely to be squirming and shifting their gaze than a child in the 10th percentile for those traits.
Exactly. So the fundamental question becomes, are we measuring a genuinely more variable autonomic nervous system, or are we just capturing a child who fidgets more?
Right.
Because both scenarios would generate a higher VarLRdiff score.
So how did the researchers attempt to disentangle those two things? Did they even try?
They did. They ran a supplementary correlation check on their data cleaning process. They calculated the proportion of missing data samples for each child.
Meaning the moments where the eye tracker completely lost the pupil due to blinks or extreme gaze shifts.
Yes. And they found that the rate of missing samples did not significantly correlate with the children's ADHD scores.
Okay, so the kids with higher attention traits weren't generating significantly more missing data than the other kids.
Right.
That does weaken the simplest artifact argument. Like they weren't just looking away constantly.
It weakens it, definitely, but it does not completely eliminate it.
Yeah.
Head movement or a partially lowered eyelid can easily distort the camera's measurement of the pupil's diameter without actually causing a missing data point.
Oh, because the algorithm still sees the pupil, it just calculates the size incorrectly due to the angle or obstruction?
Precisely. And the authors are very transparent about this limitation. The neurophysiological hypothesis and the artifact hypothesis, they just cannot be fully separated with this current data set.
Okay. So what does this all mean? Like, if I am a clinician or a researcher looking at this paper, what are the firm boundaries of this finding?
Well, the absolute hardest boundary is that this is not a diagnostic test.
Right.
None of the children in this study had an ADHD diagnosis, and the ADHD RS5 was used strictly to measure dimensional traits. No one should interpret this as a clinical tool.
Yeah, the paper actually refers to it as a candidate physiological correlate, which is, very different from a biomarker.
A true clinical biomarker requires demonstrated diagnostic specificity.
Meaning it can distinguish this specific condition from other neurodevelopmental overlaps, right?
Exactly. It also requires high retest reliability and predictive utility at the individual level. This exploratory study establishes none of those things.
Fair enough.
It demonstrates a statistically significant association at the group level across 59 children. It is an incredibly promising starting point, for sure, but it remains a starting point.
Okay, to summarize the core takeaway here, out of 4 different mathematical approaches to analyzing 90 seconds of pupil data, only the temporal fluctuation of the size difference between the two pupils showed a modest, reliable association with caregiver-rated attention traits in these young children.
Yep.
The entire informative signal lives in the instability of the asymmetry.
And that finding dictates the immediate future directions for this research. The authors outline the next necessary steps pretty clearly.
What's next?
First, integrating head-mounted accelerometers during the eye tracking. That way they can rigorously track and mathematically correct for those micromotion artifacts we talked about.
That's smart. They also probably need to utilize more engaging, gamified visual stimuli to keep the children focused longer.
Yes.
If they can extend the viable data capture well beyond 90 seconds, they can finally apply that complex sample entropy math to the other measures.
Furthermore, they really must establish test-retest reliability. Like, if a child's pupil asymmetry fluctuates wildly on a Tuesday, does it show the exact same pattern on a Thursday?
Right.
We need to know if this metric reflects a stable neurophysiological characteristic of the child or just their transient state on that specific afternoon.
Which requires longitudinal tracking over months and years. Yeah. Before we wrap up, we do need to explicitly note a couple of disclosures regarding the source material for this deep dive. As stated in the original paper, this study was supported in part by SMK Corporation. 4 of the co-authors were affiliated with SMK. The measurements took place at their facilities, and the company was involved in the study design and data collection.
Right.
Additionally, this deep dive was produced with AI-assisted tools and reviewed for scientific accuracy by a researcher associated with this study.
Good to know.
Oh, it certainly makes you look at your own reflection a little differently. That tiny continuous dance in the mirror might be telling a much bigger story than we ever realized.
Yeah.